Yeah, good morning. It's a good honor to be here today. I really appreciate this opportunity and thanks the organizers for putting together this very diverse and interdisciplinary talk. My name is Hao Su. I'm an associate professor at New York University. In my lab, we work on quite some different aspects of medical robotics, ranging from soft robots for early disease prevention, to prevent musculoskeletal injuries using exosuit, to have some guided robot for early lung cancer diagnosis, and also using robots for brain tumor ablation. So in this continuum care, ranging from disease prevention, diagnosis, treatment, and in the last about 6-7 years, we have been focusing on exosuit and exoskeleton. We developed both lower limb exoskeleton and upper limb exoskeleton, both of this kind of compliant type of actuator and also soft actuator. I think maybe for my for our research is we are a little bit more coupled between human and the robotic system. Is that maybe a little bit different than other speakers' presentation, because in particular for exoskeleton, there's a tight coupling, mechanical coupling between robotic system and human together, right? So that's the focus of our work. In our lab, we focus on use-inspired basic research. That means we want to study some start from some interesting applications. We work with medical doctors, clinicians to try to understand the unmet needs in medical setting. On the other aspect, we also want to be a little bit fundamental. Honestly, for robotics, it's more application based, right? So sometimes I feel a little bit guilty to seeing basic research, because I don't think my research is that basic. However, in the domain of robotics, we do work on, for example, actuator design, and also ranging from actuator design, mechanism design to electrical engineering, electronics, to machine learning. So really truly a full stack researcher spectrum. So for that part, I think maybe a little bit basic. We are working on some very from component to system, the whole spectrum research. So my lab is composed of researcher from mechanical, electrical engineering, control, and machine learning. And some of my students or postdoc fellows, like for example, Sana and Susan, they just found some faculty position this year and a couple years ago. So we are very honored for them to work with us to make a significant contribution to our lab. I will briefly talk about a little bit about the surgical robot. That's in our lab, we try to make a surgical robots that's very unique from, you probably know this Da Vinci surgical robot, right? So what's unique about our surgical robot? One part is that we leverage medical imaging, like MRI or CT, to see through tissue instead of this Da Vinci robot is an endoscopic surgery, basically using camera, right? So that's a major difference using like a medical imaging, like MRI, to visualize the interventional procedure. The second part is many surgical robots, they are still rigid, and we have been developing some steerable dexterous instrument to navigate inside the human body. For example, we have been working on robot-assisted endovascular intervention. Endovascular basically means the instrument goes through the vascular, right? For example, you can go through this from the arm. It's called video. So basically, the doctor can open an incision here and use the catheter to go through the arm here, right? So it can go through from the arm. It can go inside the human heart or go inside the human brain. So you can go either up to the brain or down to the human heart to do this kind of either heart intervention, also known cardiac intervention, or neuro intervention. So basically, this kind of certainly you can see it's a minimally invasive surgical procedure. And in our lab recently, we started this project about 3 years ago. We have been developing this this very compact surgical robot. So if we think about today's workshop's theme is about the embodied AI. So basically, I probably will talk about more from the hardware perspective and give you some idea, give you some sense how we design novel electronics to make the learning of the control part easier, right? Less challenging, right? So, for example, for our surgical robot, you can see this one robot developed by in a company called Corendus. About 10 years ago, it was acquired by Siemens for $1.2 billion. And I think it is still one of the most advanced surgical robot system. Again, this is also for in the vascular intervention. It can go through either from the femoral, basically from your thigh, or from the your wrist to do this cardiac, to go to inside the heart or go inside the brain. This kind of intervention. So again, maybe give you a little bit of flavor about the hardware part. Like actually, when Siemens acquired this company about a couple of years ago, one of the lessons they learned is this robot is still kind of like too bulky. This is the first issue they found that it's too bulky. The second issue they found that is this kind of instrument, right? And it's very limited. It's not versatile. Basically, it can only operate instrument with small, about like a couple instruments, no more than 5, about 3 instruments. Basically, this is very limited. It can only work with it's only compatible with some very limited number of the instruments. So that's the lesson I think Siemens found in the last couple of years. And also in my lab, I think this may be a common issue for robotics in general, right? One is how to make robots smaller, more compact, portable, energy efficient. The second challenge for robotics in general is how to make them versatile, right? So no matter when we write a paper, publish a paper, we always maybe can show some really interesting demo. But in the real world, we want the robot to be able to handle many different scenarios. Like even, for example, for the medical instrument, we want the robot to be handle instrument with different diameter, right? So sounds easy, but actually this $1.2 billion acquisition didn't really generate a lot of adoption in the clinical setting, right? So in our lab, we are trying to develop a robot that is smaller. So this is our robot in comparison with the Siemens robot. So instead of being this kind of like Siemens robot basically have 2 robotic parts. One they're like an effector type robot. The second is the robot arm, right? So we are trying to make the robot that's much smaller and possibly can be attached to the person directly. So basically called the patient-mounted surgical robot. I think honestly, I think I know like this workshop is not medical, but just a quick question for audience here. Are you more who are more computer science background? Can you raise your hand? Yeah, computer science. Yeah. What about mechanical? Yeah. Okay. Yeah. I want to make this maybe a little bit more interactive. I think like at the workshop, I think the one part that I want to maybe share, not only share the work, but also share with you the lesson we learned, right? So I think for this project, I think the key lesson we learned that like no matter as a researcher or entrepreneur, when you start a company, sometimes we start with some question, right? Start some problem we want to tackle, right? I think one important lesson that we learned is maybe you need early verification about the problem, right? If this problem really the true problem that you want to solve, right? So that's some lesson we learned, and also we learned that like even for this company Corendus, and now it's called a Siemens robotic system. So I think how to make that robot really useful, right? It's not the only limit because this company already started in Boston area. They probably have the robot at Harvard Medical School, but how to really make this really useful, not only limited in one hospital, like this premium hospital, like Harvard Medical School, but it can be used in many other locations, in Atlanta, in other, even in rural area. I think that's one lesson we learned through this project. But for today's talk, I actually will primarily focus on robotic exoskeleton. So share with you, not only the good results, but also the lesson we learned through developing robotic exoskeleton. I think if you look at any robotic exoskeleton, basically powered exoskeleton, there are two dimensions. One is kind of hardware. The design objective is how to make the robot really lightweight and compliant. So basically, we want the robot to minimize its mass, minimize the mass penalty. So ultimately, maybe the robot, hopefully it can increase human locomotion efficiency. Basically, there's one metric called the metabolic cost, right, to basically save energy during human locomotion. So that's one a hardware design objective. On the other dimension, on the horizontal axis, you can see how to make the robot more intelligent. When we say intelligent for exoskeleton, you can see there's this kind of very advanced robotic system. This is like a Rewalk. This is one of the pioneers in exoskeleton. This is also one of the very advanced robotic system from Stanford University. Definitely, they are very representative of art work, but I think the overall for this community, for exoskeleton or wearable robotic community, we found that robots are still limited to single or one or two locomotion activity. For example, walking. In this case, it's running, right? So this robot is walking. So we found that it's actually still challenging. Even we have some promising results. I think it's still challenging to design robot that really can handle multiple locomotion activities. I think in some sense it looks easy, but in practice, actually last year when I went to ICRA in Japan, I tried some robot from one company, and they are very advanced. I still found that it's still not easy for the robot to or the algorithm to recognize human intention. And because, for example, we don't only do walking or running, we do sit and stand, right? This is even not only multiple activity, but also transition. It's very challenging, right? So again, for the second dimension, we want the robot to be intelligent, but that we mean the robot to be versatile, that can handle walking, running, and transition different activities, right? So this for today, I will start with a little bit. Honestly, it's a little bit of 40-hour talk or 35 minutes. I will start a little bit more on the hardware aspect to share with you how we design exoskeleton, in particular from actuator design perspective. And for example, when we say use-inspired exoskeleton, in our case, we truly want to understand from either from clinician or from user, for example, people who have disability. Another aspect is the bio inspiration, right? To really understand nature. For example, of course, our robot for this application, we focus on the lower limb mobility assistant, right? For us, we want to really understand human biomechanics. So what's really unique for locomotion is that I think there are maybe two challenges. First, human locomotion requires significantly high torque, very high torque. For example, I have some colleagues in my department who work on soft robot. Sometimes he asks me, does that really work for your exoskeleton? Sometimes I think if we really understand the human biomechanics, actually for locomotion, for example, even for walking, not talking about the running, even for walking, ankle joint requires 120 Newton meter torque. That's really large torque. That's really large torque. That it's a significant torque requirement, right? So the second challenge is sometimes when I talk about this exoskeleton to assist locomotion, even many audience will ask oh, it looks so easy, right? Walking looks very easy, and we take that for granted, right? Why you folks spend so much time working on this? You're doing learning, you're doing hardware, software, algorithm, a lot of different silver bullets to solve the problem, right? Why? I think one problem maybe I know of course most of you probably not familiar with this, but I think this is still something I think very useful. Basically, if you think about the lower limb, I think there are at least 8 muscles per leg to control the locomotion, right? If you think about the left leg and the right leg, 16 muscles, right? It's like you are if you think about it, you're playing piano or some other, coordination of so many muscles, which is certainly not easy, right? So I think if you think about you probably can control one of the 16 signals, right? Magnitude and timing. But if you all these 16 signals, that's not easy to do this coordination, right? So I think that's the second challenge. The first challenge is very high top. The second challenge is it requires multiple joint coordination, right? So the third challenge is, if you watch this video, is you can see this is honestly, this is one of the best exoskeleton I know, like a really great engineering work. I think it's developed in Austin, right, in Texas. But if you really pay attention to this able-bodied, healthy person like us, right? But if you see what the person is doing, of course he's walking. But if you notice his hand, what he's doing, he's holding something, right? Why is he holding something? Because wearing exoskeleton can cause like a imbalance, can make walking worse, right? So even for him, you can see he's wearing a very, very heavy exoskeleton. Even this is one of the best exoskeleton. I don't know how heavy it is, but you can see this may be like 20 kilograms, right? 20 kilograms, like 40 pounds. So basically, the point that I want to say is how to make robots really lightweight and can really coordinate with the human motion. They are both very, very challenging. Even you have one of the best engineers, one of the best engineering work, in the end, of course, this is multiple joint. I think the hip joint and the knee joint, in the end, to make a robot really useful, it's not very easy, right? So that's, I think, maybe you can appreciate the work that have been performed by this community, but still very, very challenging, right? Let's dive into a little bit of detail, like for the walking requirement for locomotion for the limb, like from the ankle joint, 120 Newton meter. And actually, the speed is not very high. It's not a very high speed. But if you think about the most actuator, right? Most motors, they have very opposite properties, right? Very low torque and high speed, right? So that's exactly what we don't want, right? So that really inspired us when I started my faculty position in the first few years. About 8 years ago, when I started my faculty position as assistant professor, I have been thinking about what do we want to work on, right? There are so many aspects we want to work on. Do we want to work on like EMG signal processing? I thought about this, but found that that's a little bit too challenging, maybe. So we started to work on actuator, right? So actuator design. But there's also one point, like I also there's one point, maybe you have heard of this Steve Jobs, but when they released the iPhone 2007, I think that's what he said. Actually, it's quoted by another computer scientist. He said, people who are really serious about software should make their own hardware, right? So I found out, wow, that's exactly, we have been trying to, honestly, our strategy is maybe make the best hardware, and we do okay software, the okay control. That's our overall philosophy, right? We are not maybe of course we are not the best AI expert. That's why we are here. We want to learn from this community, learn from the reinforcement learning, maybe in general machine learning community, right? But what we are really good at is we are trained as a mechanical engineer and also electrical engineer or mechatronics, right? So that's what we are really good at. So we want to make our own hardware. And also another point I want to make is sometimes I think the hardware is truly important, because if you don't have really high performance hardware, you cannot run this whatever algorithm you want to you develop, right? So hardware and the synergy between hardware and algorithm is truly important, right? In addition to this bio-inspired actuator, we also thought about not only, for a robot, it's not only motor, right? It's also the overall robotic system. So we have been thinking about, wow, how about the robot itself, right? So if we look into the exoskeleton, in particular, when we started the lab, like everything looks so great at this robot. Oh, it's really helping people to walk again. For people who are fully paralyzed, it's really amazing design. So my staff and also my students, we ask ourselves, what can we improve, right? if you look at the state art, everything looks so great, right? So what's the contribution that we can make? So what we found that actually this robot is designed for people who are fully paralyzed, basically people who cannot walk at all, right? There's no any residual motion, all right? So this is actually a very small user population. The second limitation is very, very heavy, right? Unilateral mass is 15 kilograms, bilateral is 30 kilogram, really, really heavy machinery, right? So that's the limitation. And if we dive into the device itself, we also found that the robot is actually designed from a low torque actuator, but high speed, and I mentioned, and also they have very, very high transmission ratio, basically 200 to 1. So this makes the robot very, very heavy because 200 to 1 gear transmission, you need a lot of gears and very, very expensive gears called a harmonic drive, right? So basically, in our lab, we did something different. First, we developed some like a high torque density motor. And the second, we look into some like a softer transmission, like a cable, fabric, elastomer. And also, instead of this multiple joint, for this robot, they can power the hip joint and power the knee joint, right? For our robot, we focus on single joint actuation. So that's actually a very important kind of design philosophy, because it's not only making the motor and the transmission lighter, but also think about because for able-bodied population, we think single joint actuation is easier, is simpler to design, right? And we don't want to, even using our technology, if we design this hip and knee multiple joint exoskeleton, it will certainly double this overall mass, right? It's not, so this is something we kind of like a simple, but we really keep this in mind. Overall, we think this is really a new paradigm to electrify actuation, to make the robot really compliant, high bandwidth, high efficiency, and low cost, right? So it sounds like there's a free lunch, right? You make everything much better, right? So actually, of course, there's no free lunch. The effort to get this kind of high performance is to, for example, we need to design this high torque density motor, right? So of course, the overall performance overall is significantly much better than this traditional actuator, than this series elastic actuator. Basically, it's based on the mechanical spring to produce some like mechanical compliance, right? So we developed this high torque density motor, and it's not only high torque density, but overall it's lighter and smaller. So when we say smaller, why do we bother to make the robot smaller? The point is we want to put the robot under human clothes, right? So normally people don't want to wear exoskeleton and feel you are a machine, right? So we want to make the robot really, really small. It can be wear under the garment, right? So this is we developed some robots that are getting much higher performance in the last couple of years. And this is actuator, but on top of the actuator, we also designed the exoskeleton and exosuit. So this is our paper published in Nature. So actually, one reviewer asked us, "Is your hardware better? your result overall result is better? Is that because your hardware better?" Yeah, of course, it's hardware better, right? It's not it's an overall robotic system. It's not only but you know, in our response letter, we say, okay, it's probably because the algorithm, because the Nature paper is probably about the control algorithm, right? So we think this is our latest version, and it's really much more compact and more comfortable to wear. And then this the early version we developed about 3 years ago. Why it matters in the end is not only smaller and lighter to make it more comfortable and also like less abusive, right? But also in terms of results, if we want to publish a paper, we cannot claim it's more comfortable. You know, maybe the reviewer is not happy. We just say the robot is more comfortable, right? So basically, what we showed that is, in addition to those like a little bit more subjective metrics, we also showed that we can significantly reduce human energetics. Other groups shown that they can reduce about 9%, 10%. and our group showed that we can reach about 24%. So basically, make your walking 24% easier, right? So that's truly meaningful, and both for people like us and also for athletics, right? This if you think about sports, it's really meaningful. We want to make a robot, right? This is the red figure is our new robot design. So basically, most when you think about exoskeleton, people think about it for people with disability. Actually, about 7 years ago, we have been thinking about how the robot can be designed for everyone and everywhere. But then I mean, like, can be used for people like us, for example, sport or hiking. So actually, if you check the news, actually, globally, no matter in US, Europe, I think exoskeleton for sports is really getting really popular now. Like I think I see many news media, they are reporting this kind of like a new application in like sports. Not only for people who have disability, more general. Honestly, it's more like a consumer electronics, right? Application. I still think that this maybe there are 3 user groups. One is the people with disability. The second is worker. For example, the third category is people like us and the consumer electronics, right? I think like iPhone is basically consumer electronics. It's not only designed for small population, right? So I think that's something I think is very interesting to look into. For example, like you probably know this company is actually a spin-off from Google, and they collaborate with this well-known Wearable company, and they are making their own knee exoskeleton. It's a single joint for the knee, and also for hiking, and I said this is for sports and recreation application. But one aspect maybe I think they want to improve is how to make the robot lighter, because for example, this unilateral is about 3 kilograms, right? Still heavy, right? Think about it, if you wear bilateral, it's 6 kilograms. I probably don't want to wear this, right? So our robot is slightly lighter, but overall, I think it's still a little bit heavy, right? We're still trying to make that lighter and more comfortable. So this we have been testing this. Of course, we focus on people with disability. When we write a proposal, we start from this way and write a proposal to help people with disabilities, and we tested it in many states in America. And there's one video. See if I can play it, and if you can about our. Yeah, another application is that I think most exoskeletons for people with designed for people with stroke is some like a neurological impairment. We also look into musculoskeletal, for example, people with knee osteoarthritis. So actually, this is a much larger population. We found that the good result we found that it can reduce pain, but the bad result we found that we also look, because the pain is kind of like a subjective, right? So we asked the subjects. If it can reduce pain, it can dramatically reduce pain about 70% for walking, stair, climbing, and the sit to stand. This is the good news, right? The bad news is, I mean, maybe not the bad news is we also tested the biomechanics and basically the objective metrics. For example, the walking speed and the gait symmetry. This is something we can measure with MU sensor or motion capture. Actually, we don't see any like a real statistically significant improvement. So this is kind of like a mixed result. But I honestly, I told my students that we should report this. We should not only report the good results, we should also report everything that we found. That I think it's not it can reduce pain. Possibly, probably, I think they probably reduce pain, right? But I also want to represent the whole picture, right? We also developed some like upper limb exoskeleton exosuit to make the robot really, similar idea, but for different application, right? Of course, like a subjective objective is very, very important, but actually we found that actually subjective in the end is more important. When we write a paper, we care about the results, but in the end, we want the people really feel it's getting help, right? So I think that's actually more challenging. Even it's more subjective. Sometimes the reviewers recognize that, because if you don't feel it's useful, people don't appreciate it, and people probably don't want to use it, and abandon wearable devices in general is still a bigger challenge, right? So I will also talk about our learning simulation control. This is going to be published in Nature last year. Honestly, we feel very fortunate to get this paper published, because at the end of the year, our primary venue is actually ESME, this kind of journal conference. We again, we start from the use inspired. So if you look at the student art results from different groups, it still takes a lot of time. You need to work on their exoskeleton, work on treadmill for 1 hour. Or the second case is this is a little bit older paper, but still represents the current situation. A researcher need to switch the controller from walking on level ground to stair climbing. So we all kind of like in some sense we all realize that AI is powerful, right? So I think about 5-6 years ago, we are maybe the early adopter of AI for exoskeleton. This community, we know that is powerful, but we don't know how to do it, right? But that's one major challenge, maybe a couple of challenges. First is when we say we want the robot to be autonomous, right? It means we don't need use another researcher to switch the control, right? And also, in the end, if you think about exoskeleton control, in some sense, seems very, very easy, right? Basically, if you look at the blue line, the biological talk, the red line is the robot talk, right? The assistive talk generated by robot, right? So in some sense, it looks very, very simple, right? You just want to generate a one-dimensional signal, and it has the correct timing and magnitude, right? When you talk about the timing and magnitude, it's getting more challenging, right? And also, even we only assist, for example, a single joint for the hip joint. Actually, we need to make sure, even a single joint, you need to coordinate with other 16-dimensional signals, right? Like muscle activations, right? So how to close this sensing, perception, prediction, planning, and control loop? In particular, like it's a prediction and planning, right? It's not only know what the person is doing now, but also maybe predict maybe half second to really understand the human intention, right? That's the prediction part, and the planning is very, very difficult, right? So this is the work did my Susan and was my postdoc in my lab, and also there are actually student Megan and Sana, they are the first three authors of this paper. So they did student did this reinforcement learning algorithm, and did the experiments, and also Sana also did the experiments with students together. So basically, the overall approach is to be experiment free, right? So we don't want to do any experiments. When I put a robot on you, I don't want you to walk on the treadmill for half an hour or even 10 minutes. No, we want you to wear exoskeleton for. You don't need to wear the robot to really learn the control algorithm. So basically, we call our method model-based and data-driven reinforcement learning. So basically, the model part is we build a musculoskeletal model of the human, robot, and also human-robot interaction. So this is the model part, three components, right? Human model, a robot model, and the model between the human-robot interaction. The second part is data-driven. That actually we build three simple neural networks using very basic actor critic method. But those three networks, basically the first network learns how to the input is a human front angle. The first network converts this to human front top, right? So this is in computer simulation, right? The second network from the computer human joint does the calculation to human muscle activation, right? So this kind of like it's actually we call this fixed informed. Basically, it's explainable, right? You can see those two neural networks there. They have a physical indication. The third network is a robot control network. So it's also fully connected simple network structure architecture. And in the end, we deploy this. We want to learn this neural network policy and then deploy this to the physical robot, right? So that's the general idea. And overall, it's actually very generic framework that can be used for many applications. For example, I'm not diving into all the three networks, but basically, I think the key challenge of the key takeaway is how to formulate the reward fraction, right? I think that's the key challenge to formulate the reward fraction in simulation. And another challenge is how to bridge the sim to real gap, right? Of course, there's mismatch between model and between simulation and physical system, and also larger variability between human A to human B. So this we use something technique very simple, domain randomization. I think all the machine learning experts is so common technique, but it turned out to be very effective. And also I talked with some other another author who published in Nature too. He said actually domain randomization also works very well for drones, right? So it sounds like a very simple technique, but turned out to be very useful and effective, right? Sometimes it's amazingly effective, right? So for example, when the person does from walking, running, stair climbing, and this top profile, one-dimensional signal looks simple, but if you really do this multiple activity, it's getting really difficult and challenging, right? And in the end, we can significantly reduce the energy for walking about 24%, running for 13%, and stair climbing for 15%. This truly have like athletic performance improvement, right? Even for able-bodied population. So when the paper got accepted, we generate several artwork for the publisher, and but it was not accepted. So in the end, this is the cover, and actually, this upper fold, right? So, but our papers is here, right? So it's called like I think artificial assistance, right? So we are also part of the cover, but we are still very excited to get the paper really accepted in Nature, and also with the upper fold is really amazing work from the AI community, right? So what we are working on right now is quickly ramp up is we are developing something called exoskeletons. We are trying to further improve the performance of the simulator, right? And actually, we developed a simulator in Dart, actually developed by one faculty who was at Georgia Tech. So actually, Dart maybe I think it's still not a very common nowadays, maybe, right? So we are trying to develop a high performance simulator and also try to understand better, because our Nature work paper it works, but we don't really know why it works. I mean, we know some part of that, right? But we still want to have a better idea. The second step we want to work on is this actually learning simulation could enable maybe digital clinical trial. For example, you can use a digital twin of virtual human, like simulate a neurological gait. You can also use a digital twin of robot, right? So normally, reinforcement learning has been probably used for robot-only system, but in our case, we have like a human, not only able-bodied human, but a human with disability, right? So my postdoc evaluated work on this topic, and so I think this is really a generic framework. Also, as I mentioned in the very beginning, I think my team is more specialized in electronic hardware, but I think this is a very interesting topic that we want more learning community maybe to help us, or help the wearable robotic community to make the robot truly versatile, right? And if you think about where we are for medical robotics, using analogy with the smartphone, I think it's right now we are still in the early age, even we have a lot of advancement in this field. Yeah. Okay. Thank you. Yeah.